This is sections 9.1 sequences. So let's introduce the new terminology, sequences. So what's a sequence? If I have a list of numbers, okay, written in a certain order, and we often do this, say, using a curly brackets. So let's say I have something like 1, 3, 5, 7, 9. You see, this is a list of numbers, okay, in the particular orders, and in this case, it's actually an odd numbers. So we call this is a sequence, okay. In this sequence, we're gonna give it a name. So let's say I call this is A sub n. And notice that in the sequence like this, the we call it A sub n, when n is the n term. And so basically when I write this, you see that's given a name. And when I say A1, so that means the first term in the sequence, so in this case is 1. And A2 means the second term of the sequence is 3, the third term 5, and so on. Okay, so this sequence is called infinite sequence. Okay, because it's go on forever, right? So you keep going on and on. So quick definitions. A sequence is a list of number written in an explicit order. Okay, so it's gonna be in this particular order. We often use A sub n as a name. Formally, the notation is A sub n like this within this colored bracket. Sometimes we write n from 1 to infinity. So that means it's start 1, go all the way to infinity because it's list. But sometimes you just write A sub n without the index and 1 to infinity, so you should know that, or just A sub n. Okay, now here's another example. Let's say I have the second sequence, and this sequence I call B sub n. Okay, again, formally it's gonna be like this. All right, so the sequence is now it's 2 and 4 and 6 and 8 and 10. See, that's an even number. Okay, so that's another list. Now, instead of describing the sequence with a list of numbers in that order, sometimes it's helpful to write it in or by a formula, describe it by a formula, right? So if you're gonna write out terms, what's B1? First term is 2, second term is 4, third term is 6. So the question is, well, then what is the formula that generates numbers? So if you look at these, see at 1 is 2, is 2 is 4, 3 is 6. So you see there's some relationships there. So I can tell that the B sub n will be actually described by the formula there, 2n. So, okay, so 2n, so you can see when you plug 1 in, you got 2, plug 2 in, you got 4, 3 in, you got 6, 4 in, you got 8, so it generates this list. So a sequence can be described by an explicit list of numbers or by a formula. Now, from that sense, you can see a sequence is really a function, but a special type of functions. If we're going to compare this with, here's a function, f of x equals 2x. So what's the difference between this and this? Notice that he is a function, right? We have a function. versus up here we have a sequence. Now the formula is the same. The difference is in the sequence where n, we use n for integers actually. You can only plug in 1, 2, 3, 4, 5. For x, basically you can plug in any number. So the domain is negative infinity, positive infinity. So the domains of these functions, we talk about the domain, right? So domains of the function here is negative infinity to positive infinity. So when it comes to graphing, also the graphing, so here's the graph of f of x equal 2x, right? So we know this one. This is the line, right? With the slope is 2, so to go through this point 3 is 1, 2, right? And then it's negative 1, and go through 0, 0, and that's negative 1, negative 2, so go through this point, right? So it's a line. Now, if we're going to graph the sequence b sub n equal to n, then what happened? The n can only be integers, okay? So it's positive, it cannot be 0. So from the formula, you can see if n is 1, is 2, and is 2 is 4. So if you graph it, maybe we should do the table on the side. So you can see there's a table here. This is n, right? That is b sub n. So n is 1, we got 2, and it's 2, we got 4, and it's 3, we got 6, and it's 4, we got 8. So we're at that point. So n is 1, it's 2, so this is a point. 2, it's a 4, 3, it's a 6, 4, it's an 8. So when you graph this sequence, it will be just series of dots instead of continuous graph. You see, there's a line. So when you graph them, it's going to be dot, 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 dot. And notice that there's nothing's on the left of this side as well. No, not even on the left side of the y-axis. So it's always started 1, and then 2, and 3, 4, 5. So that's series of dots. Okay. So with that said, sequence can be thought as a real value function. You think of that as a functions, right? It's the same formula as that one. With the domain is subset of the positive integer. Okay, so that means the domain, it's not all real numbers, but it's just the positive integer 1, 2, 3, 4, 5, and so on. Okay. Now let's look at a couple example here. I have the sequence, right? So the sequence here again has the formula a sub n over n plus 2. So we should be able to write the fused terms. So let's say for that one, then what is a1? What's the first term? We plug 1 in, so that's 1 over 1 plus 2. That looks like a third. And then the second term, when n is 2, so that's 2 over 2 plus 2. That is 2/4 or 1/2. And then the third term is 3 over 3 plus 2. That is 3/5. Then we have the fourth term. Fourth term is 4 over 4 plus 2. That is 4/6, right? So you see, we can write down all the terms if we want, but we can continue, okay? And that's for a sub n. Now for the b sub n, So for the B7, what's the first term? You plug 1 in, so you have negative 1 to the 1 over 3 times 1 minus 2. Right, so that's negative 1 at the top over 3 minus 2 is 1. And there was a second term. B2 is negative 1 squared over 3 times 2 minus 2. Negative 1 squared is 1, and 6 minus 2 I have 4. That's 1/4. And then the third term is negative 1 to the third power over 3 times 3 minus 2. It's negative 1 over 9, so that'll be 7. And the fourth term would be negative 1 to the fourth power over 3 times 4 minus 2. This would be 1 over 10. And continue. Okay. Now, when you do this, oftentimes you want to figure out the pattern. So you continue to write the next number without doing the math. So for A7, right, so if you write out the list explicitly, it would be a third, second term. Notice that 2/4 I have, but I don't want to simplify, so you can recognize the pattern. 2/4, 3/5, 4/6. What's the next term? Right, you can see the pattern. It must be 5, 7, and so on. So that generate the list, the sequence. Likewise, for B7, if you can write down all the terms, see the first one is negative 1 over 1. Different color. And so it will be negative 1 over 1 and 1 over 4, negative 1 over 7, 110. You see the sign alternating to the next one, that's negative 1, and it's look like increased by 3, 13. Right? So 13 and then dot, dot, dot. All right, so that is the series, the sequence. Now, on the other hand, sometimes you're given a list, and you want to write a formula. So here's what I'm going to do. So let's say you want to write a formula for A7 here. Well, look at this. If you write out a term, so that's an A1, right? So A2 is 4, A3 is 9, A4 is 16, A5 25. You see how the 1, 2, 3, 4, 5 related to these? You can see that really the 2 squared, 3 squared, 4 squared, 5 squared. So that will be n squared. That's the formula. And you can check, right? Plug 1 in, you got 1, plug 2, you got 4, 3, you got that. So that's how we do. Now for B7, it's a bit harder. Because when you do, you have this is your A1, this is A2, this is A3, this is A4, A5. No, actually it's B1, B2, B3, B4, and B5. Now, first notice that the sign alternating. And how does the sign alternating? Look at this example over here. When the sign is alternating, you actually have the -1 to n powers there, right? Because when it switches from odd even power, it's going to be negative positive. So you know it's going to be this. The numerator, you see that just this, so I think that one is kind of easy. It's still n squared. Top 1, 2, 3, 4, 5 squared. In the denominators, this is 2, this is 1, 3, and 2, 4, and 3. How they're related? The denominator is always 1 bigger than the index n. So that will be n plus 1. So the formula will be -1 to n power times n squared over n plus 1. Right? So, and of course, for these, either you have formulas or list, you can always grab them. Okay, so you can always grab the sequence. So when you grab the sequence, let's say in this case, so if you look at here, I have the x-axis instead of y-axis, and here's 1, 2, 3, 4, 5. Here I'm using a bigger scale. Here this is 1, this is a half. So I'm gonna grab this sequence: a third, 2 fourths, 3/5, 4 6, 5 7. So this is the first term, right? N is 1, so it's 1/3. So where's 1/3? So 1/3 is there's 1/3. 1/3 is here. So it's a half. So it's 1/3. When it's 2, you have 2 fourths. 2 fourths is 1/2. 3, you got 3/5. 3/5 is more than a half, so it's there. 4, you have 4 6. 4 6 is 2/3. 2/3 is there. And then 5, you have 5 7, and so on. And then you have 6, you have 6 8. Actually, it's going too fast here. It's below. Okay, so we have this here, and 5 7 is there. 3 4 is precisely in this line, and then so on. Okay, let me graph. So in this case, notice that when you graph the sequence, you see the dots here, it's increasing. Is it increasing forever? Well, it keeps increasing, but there is a limit. There is a limit. You look back at the formula that we have here. So we're graphing that one. Notice that they keep increasing, but it won't get beyond this line. And this is what we call the limit. It won't exceed 1. How do I know? You look at this again, in n over n plus 2, the numerator is always less than denominator, so that ratio has to be strictly less than 1. But as n getting huge, if you get n to like 1,000,000, then you have millions over million plus 2, so 1,000,002. So that ratio is almost 1. Okay, so these you can see that it's getting closer and closer to 1. And so we say from this example, right, the sequence that we look at, what will happen when n is getting large? When n is getting large, I'm talking about that's the sum n getting large, right? Go to infinity. this sequence to approach a number, in this case is 1. Okay, so here's the terminology. In this case, we're gonna write limit of n over n plus 2 and approach infinity equal 1. You see, that's the same notation we use for functions. So we write limit of the sequence n approach infinity equal 1. And when that happens, we say the sequence A sub n converges to 1. Okay. Now there are times that there's no limit. Okay, that limit does exist. The sequence is said to be divergent, or it diverges. You can easily see this series right here. If you're gonna check where converge, diverge, that one diverges. That one, right? Because you see the number 41419, 1625 go all up to infinity really quick. So there's no limit. Okay, so that's the one case where it diverges. Okay, so to determine whether converges diverges, you're gonna take the limits. Okay, so here I have some properties of limits back in chapter 2. Back in Cal 1, you can look up the formula. So they pretty much the same. We can use them there. We could determine the convergence of a sequence. So here's a couple of examples. You can see we can take the limits and determine whether it's going to infinity or not, or if it has finite numbers. If you look at the first one here, let's determine the convergence of this sequence. And all I do is take the limit of n plus 1 over 3n minus 2 and go to infinity to see if that's an equal. Now this is the case where it's going to infinity, the top and bottom go to infinity. I'm going to review quickly here. So one way to do when you have rational is you divide the top bottom by the highest powers of the denominator. So you see the denominator here has degree 1, right? So have degree 1 in the denominator. So we divide by n to the first power, right? Degree 1. So we divide by n. So if you divide the top and bottom by n, then this will become limit n divided by n is 1. 1 divided by n, 3n divided by n is 3, and 2 divided by n. Okay, so we do that because from here we can see when n go to infinity, that's approach 0, that's approach 0, left with 1/3. Right, so the limit is 1/3, so a sub n converges to 1/3. Okay. Now, if you look at this is number 2, this is number 3. If you look at number 3 here, you take the limit of this natural log of n over n cubed and approach infinity. Now this time it is not a rational function, so I cannot determine the degrees and do the same. So in this case, we're going to use what we call the L'Hopital rule. So think of this as, instead of dealing with this is the sequence, right? And it could be just 1, 2, 3, 4, 5. I'm going to switch to functions. Think of that as just natural log of x over x cubed, x approach infinity. Now, when I switch to the function point of view, the reason we do that is because we can apply the L'Hopital rule. Remember, the L'Hopital rule says if the numerators, you see, when x goes to infinity, the natural log goes to infinity, the denominator x cubed goes to infinity. If that happens, you can use the L'Hopital rule by taking the derivative of the top and the bottom simultaneously. So what's the derivative of x? 1 over x. What's the derivative of this? 3x squared, right? So when you simplify it, right? So when you simplify this, you would have limit 1 over 3x cubed x approach infinity. What do you think from here? X getting large, a fraction getting small, approach 0. So your answer is 0. Right? Now you look at number 4. Last one here. Last one here, you take the limit of negative 1 to the n factorial and approach infinity. Now that one, what happened when n go to infinity? I don't have the fractions here. But if you want to examine a little bit and look at the first few terms, when n is 1, so that's negative 1 first and 1 factorial, so that's negative 1. When n is 2, you have negative 1 squared is 2 factorial. Now 2 factorial is 2 to 1. That's 2. Right, so that'll be positive 2. And 3 is negative 1 to the third power, 3 factorial. 3 factorial is 6. 3 times 2 times 1, so everything is 6. And the fourth term is negative 1 to the 4 times 4 factorial. 4 times 3 times 2 times 1 is 24. So do you notice that the signs alternating? And moreover, these numbers is increasing 1, 2, 6, 24. So what does limit approach? Well, it doesn't approach anything. It's gonna flip from negative 1 to positive 2 and then 6, 24. So it's like going like this, getting larger and larger in both directions. So it won't approach anything. So in this case, the limit does not exist. And therefore, the sequence b sub n diverges. Okay. Now, before we leave these sections, I want to do a quick review on the factorials. I believe some of you might have a big problem with factorial. Right, so don't forget the definitions when I write the n factorial. That is really 1 times 2 times 3 times 4 all the way to the next one at the n minus 1, and then the final one is n. Multiply all the way to n. Okay. Now when it's come to simplifying factorials, you might look at this. For example, you have what is 9 factorial over 8 factorial. Well, don't forget that 9 is 1 times 2 times 3 up the way to 9. 8 factorial is 1 times 2 times 3 and up to 8. And so all of these cancel. What's left? 9. Right? So it's 9. So sometimes You see that the larger the 9 is bigger than 8, so the 1 survived, the rest is gone. Likewise, if you have to simplify something like 26 factorial over 28 factorial, well, you're going to have to write everything out, but you can see the top is 1 through 26, the bottom is 1 through 28. They are identical. You got rid of all of them, except that thing on the top left, 1 through 26 got 20 cancel. The bottom is just 27 times 28 left. And sometimes we're going to simplify in general, say, what is n factorial over n minus 1 factorial. So if you compare the two, n and n minus 1, so this number is 1 bigger than n minus 1, like this, right? Top 1 unit bigger than the bottom. So when that happens, this is really 1 times 2 times 3 all the way times n minus 1 times n. The denominator is 1 times 2 times 3 all the way times n minus 1. Right? So you can see that cancel, and the n is left. And one more. So let's say to do n plus 2 factorial over n factorial. N plus 2 is 2 units bigger than n, so everything got cancelled. What's left? N plus 1, n plus 2. Right? So the largest 2. So y, the next is n, so all of them got cancelled, and that's the answer. Right, so let's finish the 9.1.